Good to see everyone. I'm Helen Altshuler, co-founder and CEO of EngFlow. You will see me multiple times on stage today, so every time I come up, I'll introduce a new awesome engineer in the Bazel community who hasn't yet given a talk here, like Eloise.
Hello everyone, I'm Eloise Pozzi. I am a software engineer at Canva, and I'm very happy to be talking to you today about Bazel data outputs and avoiding pitfalls in debugging and optimizing builds at scale. So build performance matters, right? That goes without saying. And I like this XKCD comic because, sure, waiting for your code to compile can be a good excuse to take a break or sword fight with your teammates, but in reality, those minutes add up fast. At Canva, we have started laying the groundwork to monitor this kind of idle time. The moments when developers are just sitting there, waiting for a build to finish. The goal isn't to track people, it's to find patterns. Where are we losing time? What parts of our builds are consistently slow or unpredictable? And to answer those questions, we need to look at the data. We need to understand where are things going wrong? Are we hitting some unexpected cache misses? Are there targets that are rebuilding too often? Are we hitting some non-hermetic actions? Or are there some flaky tests that just keep rerunning? And luckily for us, Bazel gives us no shortage of data. It's got logs, profiles, queries, protocols, you name it. So instead of guessing where things go wrong, let's use the data Bazel already provides us to our advantage.
Bazel was open sourced in 2015, and its beta version, it shipped with Bazel Query. Then the team internally investigated lots of build issues, and to teach the engineers how to solve their own problems, they added very helpful tools such as cQuery created by Julie and aQuery by Toby. In 2018, Jacob and Klaus and the Bazel team worked on BEP to modernize internal master log infrastructure by creating a gRPC and protobot-based APIs and shipping BEP to the build UI, all while racing for a very important demo for a customer. That was actually a fun project I also got to lead across teams at Google when Google started investing heavily in making its internal infrastructure available for the Alphabet companies like Nest. And also working with external early adopters of Bazel's companies like Wix, which were particularly instrumental in defining BEP requirements. That project resulted in improving Bazel for the external community that started rapidly adopting it around the same time. Luis and Ulf, our co-CTOs at EngFlow now, were at the time at Google very closely involved in shipping BEP, so all of us could use it now in our build analytics. And at Google, code bases continued to grow, and that meant new tools had to be developed. So in 2019, Ulf added the JSON trace profile in order to investigate Bazel client-side issues. And Sarah Adams actually gave a talk about this at BazelCon 2022 that you can see. And in much later stages, Bazel execution log was added in version 6, but we recommend using it from 7.1. You'll hear more about that from Eloise in a moment. So build event protocol mostly gives you target level and invocation level data. Target may have several actions. If target fails, you will be able to get the failure and the action that failed. It includes mnemonic, failure details, and other helpful messages, as well as BEP metrics. Its main use case is in the invocation and root cause analysis, and also you can track that over time as well. Worth noting that the last BEP event, called build tool logs, actually will tell you where you can find other data produced by the build, like where to find exec log. You may be familiar with the terms BEP and BES. So to add to confusion, BEP implementation actually has a term called build event stream, which is not to be confused with build event service. So build event service protocol is a generic gRPC service for publishing build events. The BES protocol is independent of the BEP, and it treats BEP events as opaque bytes. Internally at Google, BES is used not just for Bazel events, and also if you're working with other build systems, that may be a way to ship events to your other internal analytics tools. The BEP upload mode is another important concept to consider some of the nuances and implications of. So build event protocol events are uploaded in a continuous stream, hence the build event stream terminology that I talked about. BES upload mode is a flag that controls BEP events and how they are uploaded to this BES backend. When the flag is set to fully async, Bazel uploads BEP events asynchronously, so that means that the Bazel command can return to the user, and the build events will continue to be uploaded while the build is running in the background. The build itself is not delayed by the upload process, which of course is a win for performance and for interactive builds, but not so great for CI. So it's a reliability versus speed trade-off. At Google, BES upload mode equals fully async by default. But not everyone has pristine CI infrastructure, and it can cause issues, as we noticed. So since the upload is asynchronous and the command exits without waiting for acknowledgements, there's a possibility that some events might be lost in the background. And upload process, especially if it encounters issues, there's a higher chance of that happening. Many Bazel users use ephemeral CI instances, and as such, the daemon dies after the run. So changing to fully async by default would cause things to break. During this talk prep, Toby asked us if we should set this by default for all Bazel users, and so we said, not just yet, let us work within the community and figure out how we can avoid breaking things and ultimately implementing better tools to control the client side of Bazel. So just to wrap this up, fully async prioritizes build speed over guaranteed delivery of the BEP events, and if complete and reliable BEP data is critical, set the upload mode to wait for upload complete. In BEP, action executed, we found, is also very instrumental in root cause analysis, but only for the failed action. So it does not have the data on everything else because it would be overwhelming. Instead, you will find it in the execution log. There is, however, because Bazel is so flexible and configurable, a way for you to do that, and you can actually set this flag, build event publish all actions default to true, but should you? So one of our customers, could probably be in the room here, tried this. They adopted Bazel in 2017, so they weren't as familiar with the execution log that was added later. And so when setting that flag to true, they've seen their binary files produced went from 8 megabytes to 480 megabytes. For a single indication, a 60 times increase. So don't do that. Instead, go look in the execution log, which Eloise will tell you more about.
Perfect. So the execution log. This is Bazel's black box. It's a protobuf-based log that provides a complete and faithful record of what was actually executed during a build. Unlike other data sources, like the BEP or Bazel profile, the execution log shows exactly what happened. It captures every external process that Bazel runs, like the command line, environment variables, inputs and outputs, execution strategy, timing, and cache hits or misses. If you want to understand why Bazel behaved the way that it did, this is where you look. It makes it a highly reliable source for debugging unexpected Bazel behavior. Now, here's the catch. It's not produced automatically, so you have to explicitly enable it with a flag. So execution log binary file, execution log JSON file, or the newer and more recommended exec log compact file if you're wanting to gather the exec log more regularly. And this one was introduced in Bazel 7.1, so make sure you're on 7.1 or newer, because the compact format is significantly more efficient. To make sense of exec logs, Bazel also provides a parser, but you have to build it from source. So you can then use this to convert logs into a human-readable format, and the parser aligns actions between two builds, making it great for comparing two different builds. The log format is extremely verbose, and we have actually learned that the hard way. Like I mentioned before, Canva has started the journey to understand a little bit more about our build performance. And when we first tried ingesting some of the exec log data internally, it actually completely overwhelmed our observability system in a day, causing an incident, and this was due to the high cardinality of the data. So these logs can grow from a few megabytes to even gigabytes, depending on how many actions your build runs. That said, it is an extremely rich source of telemetry. And now that we are ingesting the data a little bit more thoughtfully, we have been able to look at spawn-related data from the exec log, like Bazel spawn duration, Bazel spawn cache hits, and some other tracing data. And we can aggregate this and slice and dice it in a matter of ways that we see fit. It has allowed us to start answering questions like, which targets could be broken up for better parallelism? Where are cache invalidations happening and why? Or where in the build process are developers spending most time waiting? It's one of the most powerful tools that we have for diagnosing build performance. But it's also a reminder that more data isn't always better. You need to sample selectively, store it thoughtfully, and know where you're looking. Otherwise, ingesting this data can become a bottleneck of its own. So let's take a look at putting the exec log to the test. So as a DevX engineer, we often get questions from other engineers like, why did I get a cache hit here, but not there? And this one from Rush is a perfect example. Hey, I was expecting a cache hit between my dev box and CI on this build. Why is it rebuilding? Now, that is a reasonable question because at Canva, our RBE cluster is shared between CI and our cloud-based dev environments. So if the inputs are identical, we should be seeing a cache hit. When we don't, it is a sign that something subtle has changed. Maybe an environment variable, a timestamp, or even a flag. The problem is Bazel's caching depends on determinism. It assumes that the same inputs always produce the same outputs. So when that assumption breaks, caching breaks too. And we start seeing unnecessary rebuilds. So let's take a closer look at the target Rush was actually running. Here we've got a simple looking Go test called paths test. And at first glance, to the naive engineer, nothing about this target seems overly suspicious. So let's dig a little deeper. Rush mentioned that she was getting a cache hit in CI. So the first thing we'll do is reproduce that build and capture its execution log. To do that, we temporarily override our CI build logic to upload the exec log as an artifact. Then we can download execlog ci.log. Next, we will do the same locally from our dev box. We'll run a Bazel clean to make sure nothing is cached locally, then rebuild the same target while passing the execlog flag again. That gives us our second execlog, execlog devbox.log, which we'll then use to compare the two runs. Now, with both logs collected, we need a way to make sense of them. For that, we'll use Bazel's execlog parser. But remember, we need to build it. So we clone the Bazel repo and build the execlog parser ourselves. Once we've got the binary, we can run it over both logs. It converts them into a readable format and aligns the actions across the two builds, so they're easier to diff. And that's what we're going to do. So after running the parser, we can now diff the two builds side by side. This lets us see where the two executions diverged. And here's what we found. Aha, here it is, a clear difference between the two environments. I can see a few sniggers in the crowd because it was pretty obvious what the issue was to us. However, to a naive engineer, maybe not. So the home environment variable has two completely different values, one from CI and one from the dev box. So even though everything else was identical, this variation was enough to invalidate the cache. And luckily for us, we were able to capture this in the execution log because other data sources, such as the BEP, don't include an environment variable log. And unsurprisingly, there is our culprit, the env inherent equals home line. By inheriting home, this target was introducing a non-deterministic input that changed between environments. The fix is really simple. Instead of inheriting home, we can explicitly set it through the target's env field to a constant value, because actually in this test, the home value was never really used. So this was a really easy win for us. But by changing this value, it makes the test deterministic again and ensures that we can share the cache between CI and dev environments. Now, the execution log graph. I think that this is a lesser known Bazel data source. However, it gives us a structural view of how actions actually depend on each other during execution. Each node is a recorded action, and the edges show how they connect. What makes this valuable is that it doesn't just show what ran, but how much each action contributed to the critical path, meaning it can quantify the drag on your build. You can then, for instance, understand how much time you'd saved if you could optimize or remove a specific node. One of the most interesting things that we learned from Google is that they use this data to understand whether the critical path is unique or one of many. So if you're optimizing an action that sits on one of several near critical paths, you might not actually be moving the needle much, as another path could immediately become the new bottleneck. Internally, they ingest this data, the execution log graph, on every build and analyze it to figure out which optimizations are truly worth it, and then throw away the data after a day because its value is in guiding decisions, not long-term storage. Moving on to another use case in optimizing builds, we can talk about adding a new dependency. And for this, often the real question isn't how long it takes to build, but it's how far the impact spreads. So, to assess the impact of dependencies in the build graph, we advise first use a Bazel query to find your most dependent on targets. These are the ones that are central in your build graph. If those change, they can invalidate a large part of the repo. Then you can combine that with some analytical data, like cache miss rates or execution frequency. And with this, you can then see which of those targets are actually triggering rebuilds. And finally, remember, a new dependency might not slow execution, but it can increase invalidation risk or fetch overhead, especially if it's large or non-hermetic. So impact is not always about runtime, but it's also about reach and build frequency.
Eloise talked about Bazel query as one of the tools also worth noting when investigating. There are actually 3 of them. Billy covered these in his Bazel training this Sunday. And to give you a sense of when to use which, we created this chart, which you can reference notes. We'll share notes from this talk as well. These queries are helpful in doing performance debugging. So you can use Bazel query to understand targets and their dependencies. It will query everything and go fast. You can use configuration query, C-query, to debug dependency graphs, and action query, A-query, to get the fine-grained details of every build for the actions for that build. Given Bazel has evolved over 10 years, so its data outputs. And so you can find similar data, but with different granularity in different data sources. When investigating cache misses, BP will give you a good high-level data, but it may not be actionable. Cache writes, for example, are useful in understanding cache miss analysis, but they're not in BP. You can find them and more other granular data in execution log. So you can combine all these tools, or you can look for other solutions. And so to make things simpler for ourselves and our customers, at EngFlow we created the RBE profile that has more consolidated and richer data for interactive and time series data analysis. So how do we construct it? We collect events which are processed while various remote execution API requests are run by our services, and we accumulate that in our analytics store. We've also optimized it for analysis with a single row per action, and we offer this as something that you can load it into your Lakehouse or OLAP tool like Databricks, Snowflake, ClickHouse, or use it in the online environment. And so to show you how this data comes together, our product manager, Jorge, created this game to teach our employees and our customers how to investigate Bazel issues. All right, let's play the game. So build forensics is what we've called it, and you are now all part of our investigation journey. Ooh, yeah. All right. So you investigate on the case, and you have a regression mystery. And over the past few weeks, you're hearing complaints that CI just feels slower. So you pull up the build times, and you look that, in fact, actually, there's P95 times are creeping up a bit. The overall cache hit, though, looks kind of stable. And so let's dive deeper into this analysis. As we talked about Bazel data, you can find different data sets in different places. So, of course, this data set that we can look at is available in the BEP, and it is also available in the RBE profile. And so the first rule of forensics is to narrow your suspects. So based on the evidence, which targets will be the prime suspects. So we'll evaluate here, and worth noting that a combination of cache misses as well as the duration is an important thing to note, because you may not be optimizing the right caches. And so as looking here, we can see that some actions are taking significantly larger hit than others. And also there is a more sharp decline in cache hits for a couple of actions here. So any guesses here, any call outs? Which of these may be the culprit and the first action to look at? I heard that there somewhere, model builder, I heard that. All right, let's do this. And in fact, that is the model builder, and it is also the fact that it's subtle, because build time is decreasing, but also cache hits are reducing more sharply than others. It is also often helpful to compare based on the additional data sets, so execution duration over time and cache hit rate over time. Again, where can you find this data? This data you can actually find in the execution log, as well as the RBE profile. And so, in looking at this chart, you can see quite sharp increase in the time, specifically for CPP compile action as well as general. And then inspecting the cache side of things, you can see that there's definitely much sharper decline in cache hits for general to 0, while CPP compile is also steadily declining. So these are certainly worth digging deeper in for analysis. And so we're going to look into these actions and keep going. So now let's start hypothesizing what is a culprit, at least for one of these. And so input file growth is often blamed for the increase in build times, and sometimes rightfully so, sometimes not. And so in this case, we can see that for general, it actually hasn't changed. So no, that's not the suspect. But for CPP compile, we could assume that there's something for us to investigate further in the input file growth, because there's certainly correlation between cache hit rate and the file growth as well. And so we'll choose this and keep going. And that takes us to a very interesting way to dig into what is actually the root cause for general. This is the data that you can see, the last 10 allocations, and what type of issues are we dealing with here. So I'm actually very curious to see also any kind of yell outs, if there's any ideas, which of these may be causing a problem here. Any suspects of these issues? Are we dealing with bad configured actions, non-determinism issues, input file dependency issues? Non-determinism, okay, and I've got that one hand here too. All right, so in fact, this is the culprit. And so we have found the serial killer of Bazel builds, because as you all know, non-determinism is in fact quite a significant one. And why serial killer? Because Eloise, in prep for this talk, told me that she's done extensive research on serial killers. And so now she knows both in life and in Bazel. So you could speak to her about that more. And so why? So Eloise showed you one example of a non-determinism issue that they've encountered at Canva. This example we see often as well. And similarly, like feel free to yell out if which of these are the culprits here. I'm definitely curious to see if many of you have seen similar issues as well. Timestamps, yes, the timestamps. In fact, that will explain why the cache hit went to 0. So it wasn't just slowly reducing, it went exactly to 0. All right, so you've mastered the case. Now you can actually play in our analytics playground, which we use on open source Selenium data so that folks can start like investigating and running queries, getting their own assessment. We also have this game you can play at our booth as well. And the analytics playground, is just to give you an idea, is going to look something like this, where you can run queries, so you can inspect the query results and look at various charts for experimentation. All right, so now that you've mastered this, you can stop by the EngFlow booth and play the game, and also you'll test knowledge of your evidence, and we'll send you Cluzel, which is our custom-designed Bazel investigation board game. Come to our game night tonight to play it, and also sign up to receive one for your office, of course, because we're relentless Bazel geeks at EngFlow. So wrapping this up and putting it together, there are various data sources. You can use them for a variety of investigations. We pulled this chart together as well, just to have a quick sheet. What data granularity is available in which source? What are the common use cases for which source as well? And so as you start learning more how to do Bazel investigations, you'll be able to use this as a quick reference. And we'll publish a blog with this information as well.
Okay, so most of the people in this room, I assume, would be DevX engineers. We are the ones who can really get into the weeds of Bazel, the build graph, the flags, the logs. But product engineers know their targets much better than we do. And that means that they share the responsibility for keeping builds healthy and fast. So we, as DevX engineers, should be encouraging teams to do a few things. Firstly, product engineers should understand that small changes in a central target can ripple through thousands of builds. And therefore, we should be advising teams to understand what depends on what. This poses the question, could a target be broken up a little bit more granularly? And what is the function of each new dependency brought in? Could we be preventing those costly rebuild cascades by copying a small piece of code from a third-party dependency rather than pulling in the entire library, especially if you're only using 1 or 2 functions? Product engineers are the best place to make these trade-offs because they understand the context of their own code. Secondly, they could use Bazel Query to stay informed. Running simple queries regularly gives visibility into how dependencies evolve over time. It's an easy way for teams to catch unnecessary or accidental dependencies early. Thirdly, ensure they are familiar with profiles to visualize performance. The JSON trace profile is a great entry point for product engineers to see where time is being spent. It's visual, it's approachable, and it helps reveal bottlenecks in the build process. And finally, build without the bytes. Flags like remote download minimal help you download only what you need, reducing some overhead and shrinking the download section in your build dramatically. So while DevX engineers can optimize Bazel itself, product engineers play a huge role in keeping builds efficient by owning their dependencies, using queries, and understanding their build data. And that's a wrap. Thank you for listening, and thank you for all of the people on this slide for their help in the research that went into putting this presentation together. Thank you.